Okay, I think I'll just go ahead and jump into it here. Let's see now. Where I left off on Monday is we were talking about this one example which involved mixed effects modeling of binary data. And what I promised, I believe, was that I'd go through this in a little bit more detail. And so we'll do that, and particularly we'll look at it in where we actually do the run and spend a little time looking over the model and R script that goes with it. And then I'll go ahead and describe what I intended to be what is labeled here as hands-on problem 2. And set you up for that, and that we'll actually be talking about next Thursday after we do the lecture on Monday. So why don't we go ahead and jump in. So some of this is going to be a bit redundant from where we were at the end of last time, so I guess bear with me if you already lived through that. So we're talking about this example where we've got we're doing a meta-analysis of some factor 10A inhibitor effects on venous thromboemboli incidence, VTE incidence. Yeah, let's see, my volume wandered down. Let me move it back up. There we go. And what we're dealing with is summary data. It's meta-analysis based upon summary data reported in the public literature. So what we've got are VTE rates from a bunch of different dose-finding trials comparing a few different factor 10A inhibitors in here. And in all of these cases, they had an active control, which consisted of enoxaparin. And let me actually open this up full screen. Oh, actually, that's not exactly what I wanted to do here. Let me switch that. Actually, what I want, they have their presentation mode. There we go. Okay, here we go. So we're gonna be looking at that. It's now we don't actually have individual binary data. Again, we're going to be dealing with summary data. So what's actually been reported is either the fraction or a number of patients that experienced a VTE in these various trials. And again, they're all compared to a common active comparator, in this case enoxaparin, with doses somewhere in the range of 40 to 60 milligrams per day. And the model we were doing, just remind you that we're going to use, because we have summary data, instead of modeling each individual patient, we're going to model the composite data, which we're going to write in the form of the number of patients with a VTE in a given treatment arm. So we've got the number of VTEs in the ICE treatment arm of the JAITH study. And that's going to be binomially distributed with parameters consisting of some probability of a VTE and the total number of patients in that treatment arm. And we modeled this as a logistic regression, so it's a logit of that probability is going to equal some function here. In this case, it's the sum of some quantity we could call a placebo effect, and then the incremental effect caused by the drug. In the drug model, we're going to have it, it's kind of it's linear in the log of dose plus 1. So we've got a coefficient to estimate here. And then we're going to have right now we're focusing on these mixed effects or hierarchical models, and we're going to have an inter-study variation component here in the placebo effect part, which is going to be nothing more than, for any given study, this is going to be a constant that's going to be sampled from a normal distribution. So we've got a normally distributed inter-study variation on this EP term. So then we're going to use weakly informative priors for all of these theta drugs here. And informative priors for the placebo effect parameters. Again, the idea here is that we have, in order to sort of characterize the placebo effects, it's difficult to do in the current trials because all of them are using active comparators rather than placebo comparators. So we're resorting to going back to historical data to construct these informative priors for the parameters on the placebo effect. Though a reminder, this is though the data I've got, yeah, most of the data in here is real. This particular component is fictional, but in principle, this is something we could do if we went back to earlier trials involving prevention of VTEs. And rather than go through the model here, let's now go to our actual implementation setting here to see first what the data looks like, and then the model we've got. Actually, let's do this here. Oh, that's right, it won't let me move that from, just a second. I always forget how to do this. Let's see if I can get it to do it that way. No. There we go. That's what I want to do. Okay, so we're into Windows world here. So I'm on the on our Windows cloud server here, and I'm in my MI255 directory. So in yours it would be a similar story. You would have an example in here that's called binomial ME example. Let's just go ahead and dig right into there. And what we've got here is, let's see, make sure did I go in the right place? Yes. Excuse me. Let's pull up the model first. Let's go ahead and do that right inside WinBUGS. Okay, let's just sort of open it up big so we can see it. Let me change something so that we don't have to see it wrap some of these lines here. I know it'll do it real quick here. I'll just do this. There we go. Okay, so remind you here, the trick we're going to be using for incorporating another level of variability in here is to actually have another loop. And in particular, let me scroll down to this second loop. Actually, let me make let's just make it full screen here. So see if I can get both loops in. There we go. Okay, so we've got this upper loop right here. And by the way, it doesn't have to be upper. Again, the order in which we put these loops doesn't make a difference. I could put the study loop down here before this. So this is looping over all the observations in our data set, and this one is looping over the studies. Oh, I forgot what I wanted to do even before we dug into this. Let me actually shrink this back down. I wanted to show you the data. Let's go back to here. Let's go ahead and open that up. Okay. To show you the data that we're working with in here. It's actually got a few pieces of items that we're not going to be using as part of this, but I just wanted to point out the key components we've got. So we have different drugs in our first column here, and in this case they're all given as character strings. We're going to have to change that to deal with WinBUGS. We've got our daily dose, so we're definitely going to be interested in that. For now, I did not take into account dosing frequency or treatment duration as part of the model, or the observation duration in this instance. Those are we're neglecting them in the example model we've got here, but conceivably those could be influential. Sorry, I scrolled over too fast. Okay, we have the type of surgery here. In this case, the two types of surgery are, and just a reminder, the reason we're concerned about VTEs here is we're talking about post-operative VTEs. And in particular, we're looking at two types of surgery that are known to present problems for VTEs. One is total knee replacement, the other one is total hip replacement, and they're noted here as either TKR or THR in the data set. We've got event types here. Now we're only worried about VTEs, but the data set also includes information about some side effects like major bleeds and what are termed here clinically relevant non-major bleeds and minor bleeds. So that information is also here. So if you wanted to, you could play around with modeling those events too, but we're only going to worry about the VTEs. We've got our event count for that particular treatment arm and the total number of patients in that treatment arm. See, do we have anything else in there that we are interested in? Oh, we have a study identifier here. So if you scroll down, you'll see that will increment. So we've got study 1, study 2, and so on, up to, I believe it's 7 studies. And the rest of this, for our purposes, we can ignore. There's some references here and comments, but I didn't give you the corresponding bibliography, so they're not going to be too useful to you. So that's the data that we're going to be working with, and the pieces we're going to be interested in then are going to be the mainly drug, dose, and the event type, because we're actually just going to take a subset of it, number of events and total number of patients, and study. So those will be the parts of interest to us. We'll have to convert that, of course, into something suitable in WinBUGS. Okay, now back to the model. Okay, so we're talking about our 2 loops. We've got our loop over observations and our loop over studies, and it's within this loop over studies down here where we introduce our interstudy variation in the placebo effect, essentially in the intercept within our model. So recall we described that our EP then as being normally distributed with some mean and some precision tau here. So we're going to do that. But now up the other part of the trick here is up in our loop over observations. We'll see in a second. Let's first of all just remind you our basic likelihood here then is just that our number of VTEs is going to be binomially distributed with some probability of the VTE occurring, and then this n here is just the total number of patients in that treatment arm. So this VTE is something we have to provide in the data set. So that's going to be some number of patients less than or equal to this n, and the n we also have to provide in the data set. Then we have our equation here. The logit of that probability equals EP plus ED, our E drug, in here. And this EP is precisely the one that we calculated down in the study loop. And let's see, somebody asked a question. Let's see what we have. The question here then is, can we just write this EP with the nested index study I is d-norm in the 1 to n-obs loop and save the second loop? And the answer is no. Well, there's a couple of things that would be a problem with that, but the main one is it would be trying to generate a new random variable for every observation, which is not what we want. We only want a new 1 EP per study. So that's one reason why it won't work. The other reason why it won't work is this a reason why it won't work? I was going to say because of having the nested index on the left-hand side, but no, actually that wouldn't be a problem. The other reason it will not work is if you try to assign a value more than once to the same random variable, you'll get an error. So that will also cause a problem. So it really does have to be a separate loop. The other, I will mention, there is another strategy that you can use besides completely disjoint loops, is there are strategies where you can do nested loops, where I'd have an outer loop that goes over study and then an inner loop that goes over the observations within that study. That is easy to do when you have the same number of observations for every study. It gets pretty messy if you try to do that in other cases. So I generally don't recommend it. It's usually simpler to code it this way and use the nested indexes. Okay, so sorry, let me mention here again. So the point here is we've got this nested index here and an item in the data set that's called study, which has to be a set of integers going from 1 to the number of studies we have, so it goes from 1 to n study. And by using that nested index, you can pick off the appropriate one of these EPs that were generated in the other loop. By the way, I've been using I as the index in both of these. That's arbitrary. You can use whatever you want as an index. I could have called the one over observations I and the one over studies J, or even used a more descriptive name if you prefer in here. The fact I used I's in both is really not important as long as they're in separate loops. It doesn't matter what name you use. Okay, so we took care of using the nested indexing along with the separate loop to deal with the interstudy variation in here. And then finally we have our eDrug component, and the other place where you see a nested index being used here, though it's for a different reason, is where we're picking off the appropriate theta for a particular drug, because we have, what was it, 5 different drugs as I recall. So we're going to have a data item called drug, which again is going to be an integer numbered 1 to 5 in this case, that has to be included in your data set, and that's what will be used to pick off the appropriate theta for a particular drug. So that's your core model in here. And then there's 2 types of posterior predictions we'd like to make. And one is we would like to make what are essentially individual predictions. Now, an individual in this context is a study rather than an individual patient. But an individual prediction then would be is where we're making a posterior prediction for a new observation in the same individual. In this case, again, the same study. But then the other type of posterior prediction we're going to be interested in is what we often have referred to as a population prediction. Again, we're talking about a population of studies rather than people. And in this case, you can interpret this prediction as representing a posterior prediction for a new observation in a new study. And because of the way we've written it here, it would be a new study that has the same design as the studies from which we got the data that we're analyzing. And in general, we'll see that the uncertainty around this individual prediction is going to be smaller than it is around the population prediction. In addition, when it comes to fitting individual data, of course the individual fit's going to more closely fit each individual than will the population prediction. And the key difference here operationally between how we generate these 2 kinds of predictions is up here, this prediction here uses the same, essentially the same probability here as the likelihood, the same probability of a VTE, which comes from this particular instance of the individual specific values for EP. Whereas in the case of the population predictions, we, in addition to running what looks essentially like the same function up here, notice that now we have a different probability term here. It's this PVTE pred, which we calculate down here using a different instance of our random effect, our EP. So it's going to be what I called here an EP pred, which again is generated down here. And now down here, notice the form of this is the same as the EP that's up here. A key difference here is this EP pred does not get used in the likelihood that's associated with the data values of VTE. As a result, this EP down here, this EP pred, is not really making predictions for the ICE study. It's making simulations, if you like, predictions for a new study that's just like the ICE study. So there's a distinction there. And we'll be using that same approach when we're talking about working with individual patients in a population modeling context. Okay, so that's the model we're going to work with. Now we have to, oh, actually I wasn't quite done, was I? I didn't show you the, let me scooch up, there we go. Didn't go through the priors. Recall we were using, I mentioned using informative priors for the placebo response, and you'll just find that these just mimic the equations that I showed you in the slides. So there's probably not too much interest in going through those again, especially since we hit on them on Monday. And then our uninformative priors for the various thetas here associated with the drug effect. Okay, now let's see what the R code looks like for this thing. Let's see, let's shrink that up a bit. Let's open up R. And go get the corresponding R script. Okay, let's go ahead and open this up. Oops. Okay, so again, a lot of this again is boilerplate. Top part, we've got our model name. That takes care of the specifics there. The rest of this we can ignore in the first part of this. Just a second, there it goes. That's what I wanted, I think. Excuse me, my Windows thing seems to have gone haywire here. Let's see if I can get it back where it belongs. Okay. It's being weird. There we go. I may have to reopen it if it keeps acting up. Okay, there we go, I think. Okay. Okay, let's just scroll on down here. It seems like the web connection's being a little slow today. Okay, so some of this is some data management here. So this is just going out and grabbing that file, the data file we just looked at. Next step here is generating another column of data that's calculating the event rate. About the only reason we're going to use that is for plots here. That's not actually used as part of the analysis. Recall we had a bunch of things in there besides the VTEs. This is just grabbing the subset of data describing the VTE occurrences, and I probably didn't even need to do this, but this is just whittling it down to the columns that we were actually interested in. One of the right now we're not going to try to model the differences between VTE events in knee and hip replacement surgery, so we're just going to do the total number of events across both surgeries, and for most of the studies it was one or the other, but one of the studies, study 5 here, you actually had patients from both categories, ones with hip replacements, ones with knee replacements. So this little gibberish that you'll see in this section down on the bottom is just summing both those and the total number of patients together to create create a data item there that's just the total number of VTEs and total number of patients in each treatment arm. So that's just a bit of bookkeeping. And finally down here, it just pulls all that together until at the end, the last statement is just kind of organizing the whole thing. So that's the data set we're going to work with, or at least that's a data frame containing that data set. And then now that we have the bug statement where we finally get all the pieces. So recall that in our first loop, we described that as going for I equals 1 to n obs. So we got to calculate n obs, which is just the number of rows that are in that data set. Similarly, number of studies. So here I use length unique, this xdata $studies. So unique just creates a vector of the unique study names in there. So in this, and then length counts up how many. So that gets us our n study. So in here we're going to go ahead and get our studies. Now comment here, because of the way we've coded this in bugs, this study variable has to be an integer sequence beginning from 1 and an unbroken integer sequence beginning at 1. If it's not already that way in the data set, you have to make it that way. One trick for doing that, if you like, is let's see, do I want to do that? We'll talk about the trick later, because I think, in fact, maybe we'll do that in the next example. But there would be various fairly simple one-line tricks you can do to get it in that form. And then down here, this one's a little more involved one, to convert our drug, which is currently in the form of a character string, enoxaparin, rivaroxaban, and so on, and converting that to a sequence of integers. And there's a function in that Gillespie utilities R script that I've given you that's called swap, which just takes a vector of values and it says, okay, convert those by using any of those that are named according to this list, the corresponding values in the second list. So in other words, in this case, any cases that are called any drug values that are enoxaparin will get converted to 1, rivaroxaban will be 2, apixaban 3, and so on in here. Then we have our dose and our VTE counts. And finally, the total number of patients in each one of those treatment arms. So that's the data that we're actually going to be passing in. For initial estimates, we have to cover all our parameters. So we've got our EP hat, our log of sigma. In this case, remember that sigma in this case is the standard deviation for the inter-study variation in EP. And the thetas is that coefficient related to the drug effects. So I guess I don't know why I only put a single constant here for log of sigma, but we could have also done some sort of a random thing also for the EP hat. Although in this case where we're using an informative prior for both of those, there probably wouldn't be much value in randomly selecting those. We're probably just as well using the center of the of our informative priors, which is what I've done here. But for our uninformative priors here, I've put some random number generation in here. Then we have to tell it what we want to look at later on, and certainly we want to look at our EP hat, our theta, and our sigma. And then some other variables that we might want to monitor for things like posterior predictive checks are going to be our individual prediction, the VTE cond, our population prediction, the VTE pred, and we might want to take a look at the probability of a VTE, and finally we might be interested in looking at the study-specific predictions for that EP, our placebo effect. So we'll go ahead and collect those. Too big a scroll. Okay. And then we have our WinBUGS part in here. So I've started out with my usual sort of defaults here of 3, 10,000, and 4,000 with thinning of 5. Again, that's we'll find in this case it doesn't take very long for this one to run. So again, that's not going to be too onerous. And if we look at it and decide that it's enough to make precise inferences, we'll run with that. If it's not, we're going to run we'll run more iterations, or if necessary, modify the model accordingly. So we'll go ahead and run that. That'll be the basis for running that. And a lot of this other is going to be our boilerplate for getting our summary stats and our history plots and so on. And then we've got some code down here to do some posterior predictive checks at the end. And you'll see, though there'll be variations on this theme, you'll see similar patterns throughout most of the examples to do some of these posterior predictive plots here, where we're going to be overlaying posterior predictions over our observed data. So in this case, we start out by doing such predictions for doing these for the individual predictions. So you can see here I've got a statement where the pred value takes on the components of our posterior samples that describe our individual predictions. So this whole nonsense with grep and so on is just grabbing the columns in the posterior matrix who have names that begin with the letters VTE.cond, which will be precisely the things we want for our individual predictions. The columns also happen to be in the same order as the observed data in our data set, so it's fairly easy for us to align those up. Let's see, I got a question here. It says, can I explain more about save model, bugs fit, and so on? Yeah. Let me see if I can get my scroll bar back here. It's hard to see do this without getting a scroll bar. Let's see. There we go. Okay, where did it go? It's right after the running of the WinBUGS. Okay, where to go here? There we go. Okay. Well, I mean, first of all, in terms of its functionality, all it's doing is taking this object, this bugs fit object, which is a complicated list of results that bugs is returning back here. So it has the MCMC samples. It has the MCMC samples for the various parameters and other monitored quantities in a few different forms in there. There's a few other things in there, like calculations of things like a mean deviance and a few other quantities that I would encourage you to actually take a look at the documentation for bugs, which is associated with the Art of WinBUGS package, and you can get some idea what the structure is. But anyway, in particular, it contains the MCMC samples for the various parameters that we've saved. And what save model is doing is it just opens up a new folder inside the place where you're inside your working directory that has a name, model name, and model name was the root name for our various model files here. And so it opens up a new directory with that name and saves this bugs fit object to it. That's basically all it's doing. And once it's saved there, if necessary, we can load it back again in the future. So let's say you run this, you've got a successful run, but you decide later on that, gee, there's some certain things I wanted to do with the MCMC samples that I didn't do the first time I ran this. So your options at that point is either to rerun the whole mess again, or you can instead go into the file inside that this thing is created and actually upload it. In fact, let me show you in here I had run this before. So here's the folder, this binomial ME example, that's inside the outer binomial ME example folder. And inside here, when I open it up, you have the various things that get saved. Well, the part that save model creates is, one, it creates the directory, and it puts inside the directory this object right here. In this case, you can see it's got the name of the model, .fit.rsave. This is an R object. It's a binary object that's fairly condensed, that contains our WinBUGS results. And so that was created using an R save command, and it can be loaded back into R using a load command. So anyway, it's saved there in case you want to reuse it later. Now if we go back to our R script, notice I've actually got a commented out load statement following that save model, and I put that there because if later on I wanted to come back and use this, I can use that load statement, uncommented of course, to pull up exactly the same set of MCMC samples and then use it for additional calculations that maybe I hadn't considered doing on the first pass. Okay, so I guess let me know if that doesn't quite tell you the full story. If you're interested in the guts of save model, just go to the bugstools.r script that's in the bugs tools directory that you have, and you can look at the guts of that to see what it's doing. It's actually, as I recall, it's a pretty short script. There's not a lot going on in it. Okay, let's go back here. Come on. Okay, let's head on back down. Let's see. So we were talking about our pred here, where we're grabbing our individual predictions here, and all this bit of nonsense here. Oops, I just moved something I didn't want to move. I gotta hit an undo. Okay, well, just wanted to highlight this. So what's going on in here is it's creating a new object here, which is it's going to be a data frame that has both the observed data and some information about the posterior predictions. And in particular, it's going to contain the posterior median, the 5th percentile, and the 95th percentile that it's going to be using for doing plots. In fact, you know what? Maybe what would be useful is for me to do a run. Let's go ahead and do that. Let's actually get rid of. Oops, that's not what I want to do. Going to the wrong operating system there. Okay, let's go ahead. Go back in there. Let's go ahead and just get rid of this guy. And one way to give you maybe a little better idea of what's inside this is to dissect it a little bit for you here. Let's go ahead and take this down to, let's just take it down to here for now and run it. Okay, so it's going to take a few minutes for this to run, but as I recall, this one is, though it runs slower than the real simplistic examples, it's not that complicated an example, so it doesn't take all that long to run. Okay, let's see, did it actually return control to us yet? Yes, it did. Okay, good. Okay, so it's returned control to us here. Let's take it a little bit further here. So let's see, what did I do? I took it down. Okay, I know one thing that might be worth doing here. Okay, let me see if I can get this whole thing in the window here. I'm in trouble with running this in large fonts and everything here, as everything runs below the screen here. Okay, so for instance, let's take a look at what the column names of posterior are here. The idea is I want to give you some idea of the data structures you're working with here, or the objects. So here's now it's a little bit long here. Let me scroll up a little. Okay, so you can see it's got a bunch of things in it. It's got the parameters we asked for. So you can see the first column is this EP hat, and then you got the thetas going from theta 1 to 6, and then you have the sigma. So those are actually the main parameters we wanted to look at. Then we have our study-specific values of the placebo effect in there. Then we've got our predicted probabilities of VTEs for all of the treatment arms. And then we go through similar things you get the predicted values for our individual predictions, the VTE conditional, and then the same thing for the VTE preds, one of those for each one of the treatment arms. And you can see there's 39 treatment arms overall. So that's what the column names look like. And in fact, one thing I didn't do, let's do dim posterior here, and you can see that what we've got, so this thing is a matrix that has 3,600 rows and 133 columns, and we just saw the list of the names of those 133 columns. So and the 3,600 then is the number of MCMC samples we've retained. So again, that's the result of doing three chains of 10,000 iterations, where we throw out the first 4,000 iterations of each one of those, and then only keep every fifth of the remaining ones. So that's where you get. So what do we got here? So you're going to have 3 times 6,000. So that's excuse me. So that's what 18,000. And then if you divide that by 5, you end up with 3,600 left. So that's what we're looking at in this thing, and your estimates of the posterior densities then come from looking at the columns of this matrix. Let's see what I was going to take you down to. Let's go to this guy. Okay. Okay, let's scroll down. So let's see, let's go ahead and do let's see, where do we start? We ended up right after posterior, so let's take this down a little ways. Let's go right to there. Let's just run that part. So you can see what's happening. It opens up a PDF device here. It grabs a subset of this SIMS array in here, which also contains our MC samples. It generates, whoops, grab the wrong thing there. Generates this P table, is where this parameter plot table function, again, you can look at that inside of BUGS tools. That's generating some plots like history plots and density plots, as well as generating a summary table, and this write CSV statement is generating putting the summary table in a file. But once we've run that, you can look at things like if I do P table, just look at that object, you can see what I actually get is my summary table for the various parameters here. So that's the same thing you get when you look at the file that was generated. Okay, let's go back to a thing here and go down to where we're going to do our posterior predictions. Let's just take it down to before we even do the plot here. Let's just generate the object we're going to use for creating the plot. Okay. So the first thing we're going to do is we generate this pred, which is nothing more than the subset of the posterior corresponding to the individual predictions. And then this next thing is creating again, it's taking the observed data and then tacking on to that these quantiles for the posterior prediction. So let me give you a visualization of that. So I called it X1. So if we look at X1, it's scrolling off the screen a bit here. Let's go back to the top so you can see what the columns are. Okay. Oops. It's a little harder controlling the scrolling when you're working offline like this. Okay, so you can see what the object looks like. It's a data frame, so just a square table. So we've got study, the drug, the dose. We've kept some of the other items from the data set like the surgery. We've got the event count, total sample size. We've got an indicator here called type, which says which type of quantity we're looking at, whether it's observed. Let me actually scroll that down. So here you can see that's for observed. If we scroll down, we'll see now we've got the 5th percentile, the median, and 95th percentile. So it's really just a repeat of the same structure, but for the observed and both the observed case and all the quantiles. And that's the structure we're going to use in conjunction with a lattice plot statement to generate the kind of graphics we want. And this somewhat cumbersome plot statement right here is going to take that information and give us a plot showing these. And probably the best thing to do is show you the plot. Actually, the easiest way to show you that plot is actually to show it in the slides here. Oops. Okay, that particular plot is this left-hand panel that we've got right here. It's a little extra complicated because I've overlaid these predictions for the enoxaparin over the top of the predictions for each one of the drugs. So the plot would have been a lot simpler if all I was showing was the prediction for the drug where we have the dose response information. And that's where you see the observed data in the circles. You've got the posterior median in blue and the 5th and 95th percentiles in red here. There's some extra complications in there because I've also overlaid the enoxaparin data. Let's see, that might be E. Which one is the easiest one to see this in? I don't know, maybe the rivaroxaban study 1. And here the dashed lines are our posterior predictions. So we've got a blue dashed line for the posterior median and red for the 95th or the 5th and 95th percentiles, and then there's a solid, I think it's a black line in there, which corresponds to the observed value for the enoxaparin treatment in that study. Okay, so I'm not even going to step all the way through this because I should probably start by explaining a simpler one. But if you pound through this, you'll see where, for example, we've got some bits here that have to do with the enoxaparin treatment itself in here, and that's sort of an extra complicating thing in this case. So that was that plot. This next plot was actually one I used to create a slide. It's probably not too much of interest. It only contains the observed data, so that's not too interesting. And then down at the end, I do essentially the same thing all over again, except notice the pred statement is got one difference, and that one difference is instead of VTE cond, it's got VTE.pred in here. So this is being used to generate exactly the same kind of plot, but for the population prediction. I think that's the end of the yeah, that's pretty much it as far as this. So actually, let's go ahead and finish the run on that. Let me go back up to where I left it off. Actually, where did I leave it off? Let me check the which line I did last. See, I did. Okay, I didn't actually run the plot statement. Okay. Okay, so let's make sure I got the right one here. Okay, so we did the pred statement and we did the little bit of stuff just below it. So we want to start right there, just before the XY plot statement. And let's just take this right to the end. Okay, everything ran successfully here. Yep, it ran right to the end. Okay, so now we should have, we have, we've created the new directory and it has all the components. We've got our, we've got the rsave part here. It's copied in both the, oh, I forgot to mention that part of what the save model does in addition to creating the object that saves the MCMC samples, it also makes a copy of the R script and WinBUGS model that were used to actually do the runs. So it gives you sort of a record of what you've done in here. Then we've got the CSV file here. Then let's see, open that up. So that's our summary table for our various parameters in here. Okay. And then we have our various plots in here. So we've got, for example, our history plots. And if we look at these, we have fairly good fuzzy caterpillars. There's a couple of the thetas that, if you really wanted highly precise estimates of some of the tail quantiles here, you might want to run a few more, but they're not looking too bad. And that's also consistent if we go back to our go back to the table. If we scroll down to the end, over to the end, you'll notice that in the effective n, some of them are reasonably large in the thousands, but we've got a couple that are falling into the hundreds. Now, a number like this in the high hundreds, you're still probably getting a pretty good precision on things like the posterior mean, but you might be starting to get some weak precision about some of the tail quantiles. So if you really needed highly precise characterizations of things like, the 95th or 97.5 percentile, you might want to run more samples to get better precision on those. And let's see which one. Yeah, that was actually the first couple of thetas where that was true. Okay, let's close that. Let's see, the second one I know was just more of the history plots. I think 3 was our density plots. Yeah, so you can get some idea of values there. So this is another way of looking at your posterior distributions in addition to what we can gather by looking at the quantiles and the summary tables. I guess we should probably get our good old Gelman-Rubens-Brooks plots, and again, these are all pretty clean. They all converge to something pretty close to 1 in the tail here. And then we get those same prediction plots that I was talking about here, that being the individual predictions, and the last one here is the population predictions. Okay, and we haven't really told much of a story around this, but of course if you wanted to, you could probably tell a story around the comparative influence of the different drugs, how they compare with enoxaparin. You might be using things like, actually let me bring that last one up. You might be looking at plots like this to try and make an assessment of, okay, what would be the what would be the minimum dose of some of these other agents that produces an effect equivalent to the standard of care, which at least at the time when these studies were done would have been the enoxaparin treatment. So we can start looking at these and getting a rough idea, and you could actually formalize that and get a more careful estimate of the posterior distribution of the dose of a new agent which is equivalent to that standard of care. So there'd be various things you could do if you were, say, in a situation where maybe you were developing one of these drugs and you wanted to make a dose selection for phase 3 and for labeling. Or if the drug performed particularly badly, you might also end up making a kill decision. If there was no such dose, or if the dose that was equivalent resulted in maybe a higher incidence of bleeds than an enoxaparin. Okay, let's see, where are we? Oh, okay. Spent more time on that than I expected, but let me take a quick breath, see if there's any questions. And if not, we'll go ahead and move on to describing our hands-on problem 2, which I'll be assigning for next Thursday. Let's see, a question I got is it for simplicity reason that the drug effect was fixed? And I'm guessing what you meant by that is that I didn't include any interstudy variation on the drug effect. Anyway, correct me if that's not what you had in mind. I guess there's probably 2 reasons. One is, yes, it's for simplicity. It does simplify the description here. The other side of it is that we've actually got fairly limited information here about interstudy differences in the drug effects, because in many cases we only have one study for a particular drug. The only exception here being rivaroxaban. So we would be relying very heavily on those 3 rivaroxaban studies to estimate any parameters related to interstudy variation in the drug effect. So it might be a struggle given this limited data to actually estimate that. Similarly, I did not bother to include some other potential covariates that we had in the data set, primarily for simplicity, because in fact the VTE incidence is different between total hip replacement and total knee replacement, for example. Let's see here. Can I enlarge that? No. Let's see if I can interpret this. I'm looking at a question from Dana here. Let's see. Does the model used here give the appropriate variation for enoxaparin doses? It says only it varies across study versus the doses of the other drugs. Varies within and between studies. Says not clear how the model does that, since enoxaparin only appears once per study. Is there an individual prediction? Okay, now I'm not entirely sure I got the full gist of the question, but I'll take a shot at it here. Now keep in mind the variability we're modeling here is, well, there's sort of 2 sources. One is there's interstudy variation, and then there's kind of residual variation. Driven by the binomial distribution. The way these things are varying across study is due to the interstudy variation, and in particular the interstudy variation on the placebo effect. So you can see as we go from So, so if we look at, actually, let me go back to the individual predictions. If we go to the individual predictions here, let's see, that was number 5. You can see that there's, as you go from one study to another, you see substantial variation in the enoxaparin result here. And in fact, you do, when you look at they are real studies, and you see some surprisingly large variations as you go from study to study in terms of the incidence of VTEs. So for example, you can go here, you've got the apixaban study 4, you're looking at an incidence of VTEs around 15%, whereas I go up here in this YM150 study 7, I've got an incidence of 40%. So those are pretty extreme differences for the same treatment in this instance. So that's, so I'm not quite sure, though I'm getting at the gist of the question. Now in here we're looking at population predictions on this plot. So in this case, the median should be the same. The median prediction should be the same for all of these. The variation about the median will be different depending upon sample size. The larger the sample size, the smaller the span between the 5th and the 95th quantiles here. Let me see if I can reread the question to make sure I'm really getting the gist here. Yeah, I'm not sure, Dana. You might, if I haven't really touched on what you were getting at, you might want to rephrase something in there, because I'm not sure I'm really quite getting what you're going after here. Because again, keep in mind that we're not modeling any inter-arm variation in here except via residual variability in here. We're not modeling anything at the level of patients. Let's see, got a couple more from Zhao here. What about intra-study variance? Well, that's basically what okay, you said thanks. I guess I answered that when I talked about the residual variation. And I tend to use probably what you call intra-study is equivalent to what I would call residual variation in here. Okay, let me go ahead and outline example 2 to get you rolling over the next week with some additional hands-on work. I'll keep my eyes open to see if you have any further questions about the example we just went through. Yeah, Okay, let's go down to our hands-on 2. So we're going back to our cystic fibrosis theme now. And in this case, we're going to be looking at a hierarchical or a mixed effects model. In this case, we will be looking at things at the, we're going to be looking at things at the individual patient level now. So the context here is we've got a phase 2 dose finding trial. And this is actually the same one that was associated with hands-on problem 1, but we're going to look at a different outcome. And we found that a number of patients reported moderate to severe coughing. And some exploratory analysis suggested that the coughing was drug-related, but that there was also a degree of tolerance. And in particular, by that I mean the incidence of the coughing reports decreased with time. And we're going to explore that by fitting a longitudinal binary model to the cough data that was observed in the dose response study, using a model where that probability of coughing can decline over time, and that could then be used to assess the strength of evidence supporting the tolerance hypothesis. And if so, you could also go the next step, which might be to explore the effects of maybe using some sort of a dose escalation regimen to reduce the AE incidence. In other words, you would start out maybe at a lower dose, and as tolerance is forming, you would also increment the dose over time in the hopes that the overall incidence of coughing would go down. So again, the study design here, again, it's the same as problem one. It's a parallel design with 100 patients per dose arm. They were given multiple doses of this ME2 at different dose levels. So we've got placebo, 20, 40, and 60 milligrams per day given by inhalation over a 24-week period. And the adverse event we're going to look at here is going to be the occurrence of moderate to severe coughing during each 4-week intervisit period. So you can imagine these patients are going to be interviewed every time they come in for a visit, which occurs every 4 weeks. We're going to get an indication either they did or did not experience a moderate or severe coughing episode. So we're just going to report this as a 1 or a 0. 1 if they did have such an incidence, 0 otherwise. Our exercise then is going to be to construct a model for occurrence of coughing as a function of dose and time. There's a data set that you'll find, so that if you go into the hands-on 2 directory, you'll find a data set called ME2 cough data. This is what the data looks like here, and what I've plotted is essentially the same data in 2 different ways. So our y-axis here is going to be the fraction of patients reporting cough, and we're plotting that versus dose in the left-hand plot, and it's plotted versus time on the right-hand plot. And you can see in the left-hand plot then the different curves correspond to different visits here, going from 4 out to 24 weeks in there, but you can see sort of a general dose-response relationship here. So certainly you see as the higher the dose, the higher the incidence. But if we look on the right-hand plot, it also becomes apparent that after that the highest incidence is occurring in our active treatments. Keep in mind this treatment at the bottom is the placebo here. But for the active treatments, the highest incidence is clearly at the 4-week visit here, and it drops pretty quickly down to the 8 and 12-week visits, such that it looks like that by 8 to 12 weeks things are pretty well leveled out in here. So that's sort of giving you that initial evidence of some sort of tolerance behavior here. So the thing we want to do is see if we can model that sort of behavior given this sort of binary data we're going to be working with. Oops, oh, I see. I forgot what I did here. This plot, notice the y-axis is fraction of patients reporting cough. This next side is the logit of that same quantity, since we're going to be doing this as a logistic regression problem, and this gives you a visualization of the essentially the quantity we're going to be trying to bring into our model. One of the things that you might get by looking at the left-hand plot is if we look at the function of dose at these various times, is the relationship looks like it's at least sort of quasi-linear. It'd certainly be hard to make a strong case for any really strongly nonlinear model here as a function of dose. Right-hand side, again, you get this same basic notion that you get a fairly quick drop over the first, 8 to 12 weeks here, and then things roughly level off. So we'd like a model that's capable of capturing that kind of characteristic. And here's the proposed model that I'd like you to implement. And what we're going to do, it's a logistic regression model, and the probability of coughing in each one of those 4-week study periods exhibits tolerance described by a model that's similar to one that that Porcher reported a number of years ago to describe some tolerance in, I forget what the effect was. I do seem to recall it was nicotine he was working with, but it was some sort of tolerance effect he was looking at the time. Proposed a fairly simple model for that, and so we're going to use a model quite similar to it. So we're going to model the occurrence of cough in the Jth patient in the ICE study period as a function of dose and time. So we've got an indicator for whether or not they reported cough. So again, it's the ICE study period, the Jth individual. That's going to be Bernoulli now, since it's just a 1 or a 0. We've got some probability of cough, and we're going to describe the logit of that probability according to the function you see on the right side. So we've got some some intercept here. I guess you could think of that as being like a placebo effect here. And then on the right hand side we've got this thing here. We've got this linear function of dose in the numerator, and then in the denominator you can see 1 plus this x tall over x50, where this x tall varies with time. And you can see it varies as a function of both dose and time. So basically the tolerance component is bigger for higher doses, but it's also changes over time. And you can see how it goes from, so this 1 minus e to the minus k tall, that starts out at 0 when t equals 0, and then it approaches and it asymptotically goes up to 1. And you can see the behavior of this is such that this x tall then starts out at 0. So at time 0, it would say the dose response would just be E0j plus alpha dj. But as as time gets bigger, x tall then gets bigger. So, but because x tall in the numerator or in the denominator is getting bigger, this term on the right is getting smaller over time. So the effect is smaller. This probability of cough would get smaller. In other words, it would have the properties that we're looking for in the tolerance behavior. One open question might be is, do you really need this dose dependence over here or not? That's actually something you could explore as part of maybe a model selection process. And in this one, again, I'm just going to put individual variation on just on the placebo component, our E0j. And again, I'll just use a simple normal distribution for that, where we're going to estimate this sort of average placebo effect with some variation sigma in here. And you can see we've just got a collection of very weakly informative priors. You can see most of these are just flat normals. In the case of the sigma, I used a fairly broad uniform. That's a reasonable one. There's other reasonable priors here you could use for sigma. One, for example, is you might use a fairly flat. You might use a flat normal for the log of sigma would be a reasonable one. Some people like to use an inverse gamma distribution instead. Let's see, was there more I wanted to tell you about it? No. No, I was going to go ahead and have you guys go ahead and tackle that. You'll find there is a model and R script already done for this. And again, I would encourage you to probably blind yourself to the WinBUGS model and attempt to code this yourself without looking at that. How much you want to challenge yourself around the R script too, I'll leave that up to you. You could sort of strip it clean and just to give yourself a basic template and go from there, or just use the one I've provided as is. Okay, any last questions before I let you go? Okay, nothing popping up yet here. I'll leave the leave GoToMeeting up for a couple of minutes here as I shut down some of the rest of the stuff and to see if anybody's still typing, and if not, I'll look forward to talking to you again on Monday.